This podcast will cover the TCP protocol and how it works to send data in a reliable manner. Sorry, I got distracted there for a minute. So what we're going to do is we're going to look at one particular TCP session. I have this capture up from something else I was just doing, a podcast you'll probably watch later on, depending on the order of things you go. But anyway, so I'm going to look at one TCP session. In Wireshark, if you click on any particular TCP packet, you can do follow TCP stream, and that will show you everything that happened in that particular TCP stream. So a TCP stream would be one session from the time the session is established to the time the session is closed, right? The session is established with a SYN, and the session is closed with a FIN. So here we have a SYN, right? The other side replies back with a SYN-ACK, and then we respond back with an ACK, or the client responds back with an ACK. This is generally referred to as the three-way handshake. I did that in air quotes in case you couldn't tell. Three-way handshake, SYN, SYN-ACK, ACK. All right, then we transferred some data and did some stuff. This particular session is a HTTP session, captured from a visit to a website, and we send some data, and then unfortunately it looks like I stopped my session before the FIN was sent. Probably not a good strategy, so maybe I should capture a new session. Nah, well, man, yeah, I don't know. Let's see if I have any fins. So tcp.flags.fin equal 1. See if I have any fins in this session at all. Yeah, okay, I have some fins. So we could look. I don't know what that is. So we have a fin we can look at, so we'll ignore the fact that I don't have the fins for my other session for now. So anyway, if we look at what happens in this session, we send the SYN, the other side responds with a SYN-ACK, and then we send the ACK, complete through three-way handshake. So other than just making sure the other side's out there, we also exchange some important information when we establish a session. We send a SYN to the port we want to connect to. If the port's listening and willing to communicate with us, it'll send back the SYN-ACK. If we look at our SYN, obviously our TCP packet, or TCP segment in this case, is riding on top of an IP packet. So if we look at our TCP protocol portion, we have a source port, normally randomly selected high number port. We have a destination port. The destination port are usually fixed number ports for servers, right? We know we need to connect to port 80 for a web server. We have a sequence number. It's showing me a relative sequence number, which we'll talk about that in a little while. Then we show the flags. In this case, we have the SYN set. If we look at this one, it's going to have a SYN-ACK set. So the SYN flag is set. The window size value is a value that controls how much data can be sent and not acknowledged yet. Checksum is rudimentary error checking to make sure the packet, the segment, did not change in transit. And then we have some options. These options are things that we need to alert the other side to so that they know how much data to send us. Maximum segment size is 1460. That means, hey, you can send us 1460 bytes of data, up to 1460 bytes of data in one segment. No operation option that's used for padding. A window scale, a factor. You know, we have this window size value in our header. And that is a 16-bit field. So if we wanted to have larger windows than 16, then can be supported by 16 bits, which is 65,535 bytes. If we wanted to have more than 65,535 bytes outstanding, then we could use the window scale factor. Say, hey, whatever value you actually have in the field, multiply that by the number. In this case, the number 4. No options for alignment, and then our final option is TCP selective acknowledgement permitted, and so that just lets the other side know, hey, you can do selective acknowledgement if you want. So we look at the SYN-ACK from the other side. That side's going to have an IP datagram from it to us. TCP header. If you look, you should probably recall from previous classes that we use port numbers to identify connections. So in this case, the traffic from us to the server was from port 4992 to port 80, right? 4992 to port 80. The reply from the server was from port 80 to port 4992. That's how TCP is able to demultiplex the traffic and get it back to the proper process. So we have multiple TCP sessions going on. We can't have multiple TCP sessions going on at any one time, and our TCP protocol running on our machines need to know, oh hey, I just got some data, which application do I give it to? And it knows which application to give it to based on those port numbers. So that identifies the session. Sequence number 0, again, relative sequence number. ACK 1, relative ACK number. And then we have our flags. In this case, we have an ACK flag set and a SYN flag set. And then we have some window size, checksum, and then our options from the server. So the server sent a maximum segment size of 1380, 2 no operation options for padding, TCP selective acknowledgement permitted is true, and then a window scale factor. So similar options to what the client sent, but they are in a different order. I don't know if you guys noticed that. If we look at our client session, the scale factor came before the selective acknowledgement. If we look at the server's response, we had the selective acknowledgement permitted before the scale factor. So there's no required order for those options in there. So once we establish a session and agree upon those items in our options, then we can do whatever it is we want to do. In this case, it's an HTTP request. And it says, hey, I want your page, and then the other side's gonna acknowledge that it received the frame, and then it's going to start sending some data down, and it's going to return the HTTP status code, right? And then we're going to make some more requests. So then we get the data back. So TCP does ordered data transfer, and the way we do that is by the use of sequence numbers. In this case, we have relative sequence numbers. So if we start at sequence number, I'm going down, sorry. If we start at the beginning, we had sequence number 0, right? So then as we go along, we're transferring data. So the sequence numbers are going to increase. So in this case, the sequence number was 1. We're transferring some data. How much data? I think it tells us somewhere. Length 1380. So if our sequence number is 1 and we're transferring 1380 bytes of data, the next sequence number is going to be 1381. So the ACK from the other side should probably be 1381. So let's see, 1381, 13. Oh no, I sent 2 segments. So I sent 2 segments. If you look here, the server sent this segment that was sequence number 1. Next sequence number was 1381, and then it went ahead and sent sequence number 1381. Next sequence number 2761. So 2761. So the ACK would be for the next sequence number. So here's the ACK, and 2761 is the next sequence number. So that is the ACK. So that's with the relative sequence numbers. I probably should draw a picture or something for that, but I don't think I'm going to do that now. Maybe there'll be a follow-on podcast talking about sequence numbers and pictures. I don't like relative sequence numbers, so we want to change that to be absolute sequence numbers. You go edit preferences, protocols, find TCP. I just clicked on it and typed the T to find TCP, and then I want to disable relative sequence numbers, right? So then I'll say okay. So now I see the real sequence number. So if we go back to the SYN, my real sequence number is some very large 32-bit number. My real sequence number from the client is some other very large 32-bit number. And the reason we do relative sequence numbers is to make it, the reason we do such large random numbers is to make it harder for somebody to guess sequence numbers, because it can be a security vulnerability if sequence numbers are easy to predict. You can then inject yourself into a session and hijack the session. So that's why sequence numbers are so large and randomly selected. So that's that. If we want to look at, I'll save that for another podcast later. So anyway, that's really what you need to know right now about sequence numbers and TCP. To point you in the right direction for something you'll need to do later. Later on in the semester, maybe final exam time, I'll ask you to do something. I may ask you to find the initial GET request. So, connect to a server, find the initial GET request. So you put a filter like this on. IP address equals the IP address of the server, TCP port 80 and HTTP, right? The initial GET request, as long as you have your stuff filtered by time, sorted by time, right? You can click on stuff and sort it differently. As long as you have it filtered by time, sorted by time, the initial GET request is going to be the first one you see, right? So click on that and then right click and do follow TCP stream and then get rid of this. And then this just shows you the packets for that TCP stream that initial GET request was in, right? If I ask you what frame was the initial GET request, the answer here would be right here, frame 18. And then if I ask you questions related to this session, such as what is the maximum segment size from the client? Well, the client's the one that sent the SYN, initial SYN, and the maximum segment size is sent on the SYN. So you would need to go look at the SYN from the client and find the maximum segment size. In this case, the maximum segment size from the client was 1460 bytes. What was the maximum segment size sent from the server? Server sent a maximum segment size of 1380 bytes. So if you don't know what you're doing, you're going to be looking for maximum segment size on this frame and you're not going to find it. So then questions, what was the server response? In this case, the server response was 200. Okay, you might get some other server responses. So whatever your packet file says, whatever your capture file says is what you need to put for the reason for the response.